I'm going to be doing a couple of problems here from the curve sketching section. And I've done, I believe, 4 in class, and you can find those in my lecture videos for fall 2016, both my Monday, Wednesday, and Tuesday, Thursday class. This is section 4.4, and I'm going to do just a few more here because they take quite a bit of time. I'm going to do number 23, which is get a good marker here. Y equals x minus 3x to the 1/3. All right, so we want to sketch this using our techniques here from calculus. So get rid of this gum. Oh. All right, so the first thing I'm going to do is talk about the domain of this function. Man, do I have any good markers? The domain of this function, remember that this is actually equal to, oh, there we go, x minus 3 times the cube root of x. That's what that x to the 1/3 means. So just want to make sure there's no problems here. And I can plug any x value I want in and take the cube root because we only have to worry about having even roots like square root, 4th root, 6th root, because then you can't have a negative under here. But as long as this is an odd root, then we can plug any number we want into that and be okay. And then of course x by itself, you can plug anything you want there. So the domain of this function is all real numbers. So that means when we draw it, we should have a graph that goes in both directions. Forever. Let me talk about the x-intercepts. So let me try and set this function equal to 0. So if I set this equal to 0, well, I can do a couple of things. I can factor out GCF out of this would be x to the 1/3 and be left with x to the 2/3 minus 3 equals 0. And then I can set each of these factors equal to 0. So when I set the first factor equal to 0, of course I get just 0. When I set the second factor equal to 0, we get moving the 3 to the other side, this, and then what I can do is raise both sides to the reciprocal power, and when I do that, what's going to happen is that you'll multiply these two, you'll get 1, so x to the first power is just x. On this side, this means we're going to take this number, we're going to cube it, which is 27, then take the square root. Yeah, I can just do that. Square root 27. And there's other ways you can break that down a little bit more, but I really am just interested in whether or not, or where this is on my number line. So as an approximation, I'm going to use my calculator to take the square root of 27 and get approximately 5.196. So I have an x-intercept at 0, and I have an x-intercept at 5.196. So I'm going to put those up here because I'm going to erase all this. I have an x-intercept at x equals 0 and at x equals 5.196. Now, as far as a y-intercept is concerned, what I need to do is plug 0 into the function. And so for the y-intercept, I just plug 0 in here, and obviously I get y as 0. So that actually corresponds with the x-intercept of 0. That means the origin. I have a point at the origin. All right, so I've got my x and y intercepts. We could discuss symmetry here. In terms of symmetry, what I could check is to see if it's even, right? So I could ask myself, is this an even function? And that would mean that f of x would have to be equal to f of negative x. And let me just check to see if this is true. This is, I'm calling this my function f of x, okay? So my notation's right. So if I just plug in x, I just get the original function. And is that equal to, this is a question, the same thing as plugging negative x in. So if I plug in negative x here, I'm gonna get a negative x. And if I plug in a negative x here, when I take the cube root of a negative number, my answer is gonna be negative. So I can bring that negative out and make that a plus 3 cube roots of x. So now at this point I check, are these the same? And they are not. So since these are not the same, it's not even. I could check to see if it's odd by seeing if negative f of x equals f of negative x. So if I go and I change the signs of this here and here, that becomes negative x and then plus 3 cube roots of x. And the question is that equal to this? Well, we just did that right here, so it's the same thing we had up here. The f of negative x is this. Are these the same? Yes. And that means that when I graph this function, it should be a reflection over the origin. So, for example, if it does something like this over here, imagine reflecting it over the x-axis like this, and then reflecting that over the y-axis. It's not a good picture, but it's kind of like this is flipped and this is flipped. My final picture should look something like that. A reflection over the y-axis, then the x-axis. So we'll just keep that in mind, that we have symmetry over the origin. And how about asymptotes? For vertical asymptotes, I look to see if I ever get division by 0, if I ever get a fixed number over 0. But I don't even have any fractions here, so this is not applicable, so I don't have any here. And for horizontals, I'm going to take a limit as x goes to infinity and negative infinity. So what happens as x goes to infinity of my function? So I'm going to write it like this. Okay, so we obviously get infinity minus cube root of infinity is still infinity, times 3 is still infinity. So infinity minus infinity is what I'm looking at here. And that still is an indeterminate form. So whenever I saw that in the past, what I did was factored. So I can pull out that x to the 1/3 like I did earlier when I had set it equal to 0. Just rewrite the function. And now at this point, if I let x go to infinity, the cube root of infinity is infinity times infinity squared, cube root, still infinity, take away 3, still infinity. So now I have infinity times infinity, which goes to infinity. So this is going to infinity. So that means when I draw this function out the right side, it's going to go up forever. And now I'm going to do the limit as I go out the left side. So I'm going to do the limit as x goes to negative infinity. So I take the limit as x goes to negative infinity of, and I'm going to factor it again because I know I'm going to need that. Okay, so if I take the cube root of negative infinity, I get negative infinity right there. Times, now here's where things are a little different. When we do this to the 2/3, we're going to take a negative number, right? A very big negative number, we're going to square it, which is going to make it positive. Then we're going to take the cube root, which is still positive. So we get positive infinity, take away 3 is still positive infinity. So you have negative infinity times infinity, that's negative infinity. So that means the left side, or as I go out the left, it's going to go down. And that makes sense because remember, this was supposed to be an odd function, symmetric over the origin. So if the right side's going up forever, then if I reflect that over the y-axis, and then over the x-axis, that means that should be going down forever. And that's what that says. All right, so I'm going to just kind of summarize what I had up here. I'm just going to put up here that, out the right side it's going up, left side it's going down. This is an odd function, right? So it's symmetric over the y-axis. I'm sorry, over the origin. All right, now the calculus part, the derivative part. So I'm going to try and figure out where the function's going up and down, where it's concave up, concave down, inflection points, local max, local min, all those sorts of things. So I'll need the derivatives. So the derivative of this function is pretty clean. Derivative of this is 1. And then derivative of this, I'll bring the power down. That'll be 3 times negative 1, or 3 times 1/3 is 1, but it's minus, so minus x, and I subtract 1 from that, and I get negative 2/3. And that's my first derivative, but I'm going to rewrite it like this, dropping the x down with the negative exponent. And I know I'm going to be setting that equal to 0, so I'm going to get a common denominator now. So that means I'm going to multiply top and bottom here by x to the 2/3. That gives me x to the 2/3 minus 1 over x to the 2/3. And that's my first derivative. I'm going to set that equal to 0. So if I set this equal to 0, that means all I have to do is set the top equal to 0. So I set x to the 2/3 minus 1 equal to 0. I move the 1 over, so x to the 2/3 equals 1. And now I can raise both sides to the 3/2 again. Raise it to the reciprocal. And that's just going to give me x. And then over here, 1 to the 3/2 is still 1. So I get x is 1. And then if I look to see where the derivative is undefined or where it doesn't exist, I actually do have a problem here. X is 0. So you can see right here, can't plug 0 in. You can see here, I can't plug 0 in. You can see here, I can't plug 0 in. So x is 0 is another critical number. Both of these numbers are critical numbers because they're in the domain of the original function. Remember, the domain was everything. So once I have that, I go to a little picture. I plot these numbers on a number line. That partitions my number line into 3 sections. I'm going to pick some test points here, and I'm going to plug these test points into the derivative. So let me plug negative 1 in, let me plug 1/2 in, and let me plug in 2. So let's try and do this without actually going through too much work. I guess I'll plug it in right here to this one. So what would happen if I plug in negative 1? Well, if I plug in negative 1, hold on a second. 1, yeah, negative 1. Is that right? 1, I'm going to get, interesting. I'm getting 0 minus 1 into the derivative. I'm getting 0. Let me go backwards. Let me do the 2 first. I'll do 2. I'm running into a little bit of an issue here. If I do 2 squared is going to be 4, and then cube root of 4. So if I do that on my calculator, I see the problem. I've got an issue. Hold on. Back up. Right here. Might be better if, when I was right here to remind us that this meant cube and then take the square root, right? That's what that meant, cube and take the square root. So this could have been plus or minus 1. That's my mistake. Think of it this way. X squared cube root equals 1. That's what this is saying. So that means that if I took 1, of course, this would be true. But if I took negative 1 and squared it and then took the cube root, this would also work. My mistake. So that means we actually had 2 critical numbers, and one of them was negative 1. 2 critical numbers from that one, and then the critical number 0. So we have a total of 3 critical numbers, which means we need 4 test points. Negative 1/2 here. All right. Okay, now that we got that squared away, let me plug them in. So negative 2 in here. If I take negative 2 and I square it, I get 4. Cube root of 4. So I'm going to go 4. Cube root of 4 is about 1.58. So if I plug in negative 2 here, I get 1.58. Take 1 and divide it by that. get 0.69. So 1 minus 0.69, that's a positive number. That means my function is going up here. And also, if I would have plugged in 2, I would have got the same thing, because I would have been squaring it to begin with. So it's the same as plugging in -2. So I know I'm going to be going up here. At 1/2, let's try 1/2 in here. If I plug in 1/2 here, 1/2 squared is 1/4. And then we take the cube root of 1/4, and we should get, whoa, I did that wrong. I'm messing up here on my calculator. Okay, so I'm going to go 1/2 squared is 1/4. And then I'm going to take the cube root of that. And then I'm going to do 1 divided by that. I keep doing this wrong. Okay, so 1 divided by that. Okay, I get 1.58. So if you take 1/2 or -1/2, plug them in here, and then take 1 divided by that, you're going to get 1.58. So 1 minus 1.58 should give you a negative number. So we're going to be going down here and down here. All right. Sorry about that. Totally overlooked that. Got to be careful with these rational exponents. Okay. Got to be careful, because if you're doing a 2 down here, you're basically doing a square root, and you have to do plus or minus. All right, now I think we can look at this. We have a local maximum at -1. We have a local minimum here at 1. So let's write that down. I have a local max. It's happening at the point -1, and then let's actually plug -1 into the original function. If I plug in -1 right here, I get -1. The -1 here, cube root of -1 is still -1. So we go -1 minus 3 times -1, that's the same as -1 plus 3, that's 2. So I should get a 2 there. Then I have a local minimum, and that's going to happen here at 1. So if I plug in 1, this time I get 1, and then 1 here to the 1/3 is still 1, so it's 1 minus 3, you get -2. There you go. All right. That's everything I've got there from the first derivative. Now let me take a look at the second derivative. So to take the second derivative, I'm going to go back to this one right here and just do the derivative again. So derivative 1 is 0, derivative this, the -2/3 pops out, becomes a positive 2/3, and then x to the, I subtract 1 from that, so I get -5/3. This is the same as 2 over 3x to the positive 5/3. And for that one, it's pretty clean, so there's not a whole lot I need to do to clean that up. I just leave it like that. I figure out where it's 0, and that is not going to happen because the numerator can never be 0. And then I look to see where it's undefined or where it doesn't exist. And that's going to happen at x is 0. And that's it. So I have one critical number from this. I'll put it over here. It's at 0. Split my number line up. Take a test point like -1. Take a test point like 1. Plug those into the second derivative. So if I plug -1 in here, I'm going to raise it to the 5th power, which means it's still -1. Take the cube root, which means it's still -1. And then multiply times 3. So it's negative on the bottom, positive on the top. And that means I have a negative, which means we're concave down. And if you plug in 1 into that, you'll get positive. So you'll be concave up over here. I have an inflection point at 0, 0. Now that's just looking here. I changed from concave down to up. At 0, 0 of course is in the domain of the function. And so I plug 0 into the original function, I get 0. So that was that x-intercept, y-intercept point. That's actually an inflection point. So now I'm going to graph this. And to graph this, I think I'll do it right over, well, I'll do it right here. I'm going to draw a number line. I'm going to put all my critical numbers. So I had 0 here, 1, -1. This is where I draw that table. This is how I do it. So here, so I've got F prime is going to be on this row, F double prime is on this row, and F is on that row. So now I go up till I get to -1, then I go down. I stay going down till I get to 1, then I go back up. Then as far as concavity, it's down, down, up, up. And so put this together. Go up the frown is the left side. Go down the frown is the right side. Go down the smile is the left side. Go up the smile is the right side. So that's what the individual pieces of my graph should look like, these up here. And now below this, I'll draw my graph. So I know at 0, here's my y-axis. Here's 1. Here's -1. I know that some points I have here, oh wow, I have an x-intercept at 5.196. That's way out here. So I don't need this anymore. Let's just say that this is 5, and let's just say that out here is 6. So I know I have an x-intercept here. I know I have an x-intercept out here, 5.196. I know that I have a local maximum at -1, 2. So I'm going to say this is 1, this is 2. So I have a local max here. I have a local minimum at 1, -2, which we'll say is here. And that's pretty much it. Let me see here. Something is not right. -1, 2. X-intercept. I don't know why this problem is causing so much problems. Give me just a second here. It's definitely Friday. Let's see, I am recording. Thank goodness. Shoot. Why am I missing? I'm missing an x-intercept here. Oh, I see. Okay, I see what. I did it again. Darn it, my x-intercepts. See, what's making me concerned is the fact that I'm supposed to draw like this and come down like this, which means I've got to have an x-intercept. So let me go back to when I set the original function equal to 0. I can already see what I did. Pulled out a 1/3, x to the 1/3. When I did that, I had not 1, geez, Robert. I had x to the 2/3 minus 3 equals 0. We set that to 0, we got 0. When we set this to 0, we had this. It's exactly the same thing I did earlier. This means squared, so let's get rid of the squared. So I take the square root on both sides. And when I do that, I have to do plus or minus. So I do that, it gets rid of it, I get x to the 1/3 here, equals plus or minus root 3. And then I raise both sides to the 3rd power. So when I raise this to the 3rd power, I'm going to get root 27. So it's plus or minus root 27. So plus or minus. Another way you could see this if you wanted to, you could have looked at it like this. This is the same as the cube root of x squared equals 3. Then square root, plus or minus, and that's where you get it. So, I'm sorry, it's Friday. I actually just ate a big turkey dinner at lunch at my daughter's school. So I've got that, what is it called, tryptophan or whatever in my system. Sleepwalking up here. So that means I gotta go this way, -5, and here's -6, so I have another x-intercept here. All right, I know that doesn't look scaled properly, but I'm out of room on the camera, so that'll work. All right, so I've gotta go like this, and down through there, I've gotta look like that, so it's gotta go like that. And remember, it's gotta go down to infinity, negative infinity. Then between here and here, it's gotta look like this, so. And then once I get here, it's gonna switch, concave up. Once I get here, it's gotta go up through this point right here. Whoa, okay. That's supposed to be concave up. And that's it. All right, hopefully I'll be a little sharper on the next problem. All right, the other one, I'm gonna do 39. Y equals x e to the negative x. All right, so let's talk about domain. Remember, this is the same as x over e to the x. So you can drop that e to the x, or e to the negative x down. And when I look at the domain of this, I need to be careful because I want to make sure the denominator is never 0. But e to the x, if you just graph e to the x by itself, this is the graph, that's never 0. So your denominator can't ever be 0, which means that the domain of this is all real numbers. All right. In terms of x-intercepts, I can set the equation equal to 0, which just means set the top to 0. So x is 0, it's an x-intercept. Y-intercept, we replace the x with 0 and I get y as 0. So again, the origin is a point on my graph. Symmetry, you can check it for yourself. For symmetry, you're not going to have it. It's not going to be even or odd. And I won't check it. Just plug in negative x, see what you get, compare it to that function without the negative x, and see what happens. All right, vertical asymptotes. So do we ever get fixed over 0? Well, I can never make that 0, so there's going to be no vertical asymptotes. Horizontal asymptotes, now that I'm going to have to work on. I need to take the limit as x goes to infinity first of x over e to the x. I get infinity over infinity, which means I can use L'Hopital's rule. Take derivative of the top over derivative of the bottom. And now do the limit again, and we get fixed over infinity, which goes to 0. So I know as I go out the right side, I'm going to flatten out towards the x-axis. If I go to negative infinity, things are a little different. If I go to negative infinity, the top goes to negative infinity, but the bottom, you have to be really careful with. This is going towards e to the negative infinity. And what that really means, so this is a division, what that really means is that it's going towards 1 over e to the positive infinity. And that goes to 0. So the form I'm getting here is negative infinity on top over 0 on the bottom. And so that's going to just blow up. It's going to get huge. This is not infinity over infinity or 0 over 0, so I can't use L'Hopital. Another way I could visualize this is to go back to the original right here, okay, and do that limit as x goes to negative infinity in this expression, x e to the negative x. So let's see what happens. This goes to negative infinity times, now if I plug a negative infinity into here, negative negative is positive. So this is really going to e to the positive infinity, which is just infinity. And so you get negative infinity times infinity, that goes to negative infinity. So see, this was negative over something going to 0, and this is always positive because e is always positive. So this would have given you negative infinity, which is the same result we got here. So that means out the right side, it's headed towards the x-axis, but out the left side, this thing is headed down to negative infinity. All right, I'll keep that in mind. In fact, what I'll do is I'll just draw a little picture of what's going on up here. I know that it's flattening out towards the x-axis here, and over here it's diving down. It might be coming up from the bottom over here, but I just know it's flattening out towards the x-axis as I go to the right. So let's take some derivatives now. If I take derivative of this, say that function's f, and f prime of x is, you have some choices here. I'm going to do quotient rule. I'm going to do quotient rule on that. So derivative of the top is 1 times the bottom, minus the derivative of the bottom, which is itself, times the top, all over the bottom squared. So this is just e to the x minus e to the x times x over e, well, I'll do it this way, e to the x times itself, e to the x. Watch, you'll see why I'm doing that. Factor out a GCF on top. Cancel one of these. So you get 1 minus x over e to the x. There's your first derivative. And so now, when is the first derivative 0? That's when the top is 0, which means x is 1. When is the derivative not exist? And that's when the bottom would be 0, and it doesn't happen because e can never be 0, or e to the x can't be 0. So we only have one critical number. It's at 1. Now I plug in some test points, so like 0 and 2. These are going to go into my derivative. 0 in here, I get a 1 on top. E to the 0 is also 1, so we get 1 over 1, that's positive. And when I plug in 2, I get 1 take away 2, that's negative 1. E squared is still positive, so we get a negative over positive, that's negative. So I have a local maximum at 1, and now I take 1 and plug it into the original function, 1 over e, which is really 1, and then 1 over e, the reciprocal of e, .367-ish, it's approximately. All right, now I need to find the second derivative. So for the second derivative, I'm going to do quotient rule again on that. Derivative of the top is negative 1 times the bottom, minus derivative of the bottom is itself, e to the x times the top, all over the bottom squared. I'm going to do it again like that because I noticed that on the top I can factor out an e to the x from here and here. That will leave me with I'm just going to rewrite what I had here. Where was that at 1? It was at 1. So I have e to the x factored out. That leaves me with a negative 1 there, then minus this whole factor all over e to the x times e to the x. Cancel one of those out. On the top I get 1, and then I'm distribute through. So it's going to be 1 minus 1, which is negative 2, and then minus minus x is plus x over e to the x. Then I ask myself, all right, when is that 0? And that happens when x is 2. When does that not exist? That doesn't happen because the denominator can't be 0. E to the x can't be 0. So x is 2. I'll do it way over here. X is 2. That's my critical number. Pick some test points and plug them into the second derivative. So 0 into here. I get a negative on top and I get a positive on the bottom. So I get negatives, that's concave down. Plug in 4. I'm going to get a positive on top, positive on the bottom, concave up. All right. This one's really not too bad. So now, draw my chart. All I have on here is, let's see, 1 and 2. Function's derivative, function's second derivative, the function itself. So I'm going up and then down to the right of 1. And then concavity switches at 2. It's concave down, down, then up. So I'm going to go up a frown, that's the left side, down a frown, that's the right side, down a smile, it's the left side. Now I'm going to come try and draw my graph. Here's 1, here's 2. 0 is over here, here's my y-axis. Now I have an x-intercept at 0, 0. And that's the only x-intercept I have. I have a local maximum at 1 and then 0.3. So let's just say that this up here is 1. Here's 0.5. So 0.3 is somewhere around here. Now you know what I didn't do is get the inflection point. I didn't actually get what it was. The inflection point is what happens when I plug in 2. When I plug in 2 into the original function, I get 2 over e squared. And that's going to be, oops. .271, something like that. So when I go here, this was 0.3, so here's 0.5, 0.36, I don't know, somewhere around here. And then at 2, I'm at 0.271, so I don't know, somewhere around here. All right, ready to draw. It's got to look like this between here and here. And remember, I'm going to go down to the left forever, so that makes sense. Look like that. Then between here and here, it's got to look like this. And then from here on, it's got to go like this, and it has to flatten out towards the horizontal asymptote. So let me draw this piece first. It's going to go down like this. And then from here to here, it's got to look like that piece. So it's going to be kind of hard to do, but there we go. Something like that. Maybe if I would have spread it out a little more, like made it a larger y-axis, it would be easier to do that, but that's pretty much it. I did those problems by request. And I think that's probably okay right now. Just looking to see if there's anything interesting going on with any of these other ones. They're all interesting. Every single one of these has their own kind of inherent issues that can make them a challenge. Okay, yeah, let's just say that's it. Sorry about that thing on 23, kind of got messy on me. I forgot that plus or minus on the square root.